Happy Friday, guys. Sorry I missed you, but I did make a video in my absence, so hopefully you'll enjoy that, and then hopefully you have a good weekend afterwards. Today we're going over domain and range, and you have a packet that you can follow along with. You can wait till after the video or during the video, and feel free to watch the video as many times as you like. What we'll be going over, a few definitions to begin, and then I want to cover graphic identification, algebraic identification, and then one contextual extension. Okay? So starting with these definitions, before we can define the domain and range, we have to define a set. And that's just a collection of numbers. So that can be a list of numbers like 1, 2, 3, 4, etc. Or you're probably more familiar with something like this, right? Where we have a whole collection of numbers between 1 and 2 and 2 and 3, infinitely many just packed in there together. So the domain is going to be a set, and the range is also going to be a set. And when we're looking at our graph, the domain is going to be our x values, and the range is just the y values. So that's anything we can plug in for the domain, and anything that we will get out for the range. And yes, there will be functions where you can't plug everything in. One of the things that we're going to talk about later in the video is a restricted function, where there are points that you can't plug in because we're restricting it. And then, of course, with the range, you can look at a function and it's not always going to produce some numbers. But before we jump forward, we have to look at interval notation, because that's how we represent a set. That's how we'll represent our domain and range. And that's always listed with two numbers, an upper and a lower boundary. And that's going to be either with a closed bracket or an open bracket, indicating with a closed bracket that we are including that boundary or that we are not including that boundary. So with this example, we have 1 to infinity, because we're going from 1 on to infinity on the right. And we are including 1, as with this closed circle. And we're not including infinity on the right. We will never include infinity. So anytime you plug infinity into your interval, always use an open bracket, because that indicates that we are not including that number. So I'm going to jump to Desmos and show you a few things there really quick. I'm going to open this up so we can list out our domain and range as we go. Okay, so here we have vertex form of a parabola. I made it so we can use these sliders to shift the graph left, right, up, down again. And what I did for this graph, I highlighted in blue on the y-axis and the x-axis all the points that are included in our range in the y-axis and domain on the blue axis. Because remember, domain is all the x values that we can have. The range is all the y values. So let's start with the domain. No matter what I do to this, the domain for this parabola, this unrestricted parabola, is going to be everything. And that should make sense, because all we're doing is we're subtracting a number and we're squaring it. So you can plug in negative a million, positive a trillion, whatever you want. So for our domain here, what we'll have open brackets, negative infinity, comma, infinity. Because we're starting all the way at negative infinity, and we can plug in everything all the way to infinity. What about the range then? Well, as we move it left and right, that's not going to change the y output. But as we move our graph up and down, that will change. So if I put this, I'm going to put our vertex at a height of 1. Okay, so notice here that our range lines up directly with the vertex. They're both at 1 right here. And that's because no matter what x value I put in, I will never get anything that's lower than 1. I will never get any y value that's less than 1. However, depending on which x value I plug in, I could always get something that's equal to 1 or greater than 1, depending on which x value I plug in. Either way, I'm going to go over here and I'm going to use a closed bracket for our lowest point in our range, which is going to be a 1. And again, that's associated with our vertex. 1, comma. And as you might imagine, we are extending upwards to infinity here. And that's pretty clear, just like the domain extends left and right to infinity. So I do want to jump. I have one graph of a semicircle here, one that I can move around also on this, with the highlights also for the domain and range, just to show you guys that we can look at domain and range for any type of function. It doesn't have to be quadratic. So for example here, with this semicircle located right here, our domain is going to be from -6 over to -2. Right? So we're looking at x values. X is measured horizontally. So as far left as I can go is -6. And then following the graph, as far right is a -2. So here we go. Close brackets because we're including -6, comma, -2, also included. Range is very similar. Again, we're just looking for the least value, the lowest value that we can have in our output, all the way up to the highest value. So we're looking at 4 to 6. Close bracket, 4, comma, 6. That's all we're doing for this. I also want to make note of a restricted domain. So what we have here is our parabola. This is unrestricted parabola. What I do to restrict it, and in math and in life, you restrict these equations for various reasons. But what happens is you create a certain boundary, and I'm saying this equation is only going to be true within this boundary. It's a way of defining a function or an equation. And in Desmos, what we can do, we go in, and you go over to your curvy brackets right here. So it looks like that. And then we just type in our lower boundary. I'm going to go from 0, less than or equal to, x, less than or equal to, pick your upper boundary. I'm going to go to 3. And look what we have. We have the furthest left is 0, and the furthest right is 3. So this is the same parabola that we had before, but it's just restricted to those x values. So, as you can imagine, our domain is going to be from 0 to 3, because that's what we chose. That shouldn't be too hard to find. But then how do we figure out our range? Well, if we're looking at the graph, it shouldn't be too tough. Our vertex is still the minimum point, and we haven't cut that part off, so that's going to be -1. And then what about our maximum point? Well, here we can just click and see that it's a 3. But what would you do if you couldn't click and see that it's a 3? Well, we know that our x value is 3, right? So if we plug the x value in, 3 minus 1 is 2 squared. We have a 4 minus 1, which makes a 3. So we could just plug in our x values and we would get our two y values for this point and this point. And it's important, especially if you don't have a graph that you're looking at, to plug in both endpoints, because you can never be sure which is going to be part of your boundary until you actually see it. Okay? I just wanted to go one more time. I'm going to use those sliders that we used the other day. I'm going to put an A here and a B here, so we can see our sliders. And I'm going to turn on these highlights just so we can see really quick some of the things that we can do. So notate, there are some cases where I could cut off the vertex. In this restricted form of our quadratic equation, there's no vertex. So I would have to plug in the left value and the right value. And that's how I would find the range, right? Oh, and actually, this range is not accurate. But needless to say, yes, it changes, and you just have to pay attention to what your graph is looking like. Okay, so lastly, I just want to go over one real-world example, and that's this one right here. So what I'm starting with, I have a cannon. It's shooting a cannonball over to this wall over here, where it will hit the wall. And I'm going to widen this up so you guys can see it a little bit better. Okay? The example that you guys have in your packet, I think, is back to the basketball problem that we did on Tuesday. But what I'm asking you to do here, I'm asking you to restrict your function. So restrict it to some place that makes sense. Because what we do with quadratic equations in real life is we use them to model different things. And in a lot of cases, it doesn't make sense to model a cannonball that goes below ground level. And of course, it doesn't make sense to model a cannonball that started behind the cannon, right? So in Desmos, what I'm going to do the curvy brackets again. I'm just going to say that this ball started at 0. I'm going to put in the x. And I know that the wall is over here at 20. So 20. And that should do it for the restriction. So once you guys put in the restriction, I just ask you to explain why you chose those values, because you're going to have to choose a place to restrict it at. And for me, I think this makes sense because that's where the ball is leaving the cannon. And then over here, it's where it hits the wall. You know, a lot of times this will be pretty intuitive. And then, of course, we have to change our domain and range. Well, the domain is going to be from 0 to 20, because that's what I defined it as. But then the range, the lowest point, over here we have a 2. And over here, we happen to also have 2. So it's going to be from 2 all the way up to 4.5. Okay? So I'm going to jump back really quick to the PowerPoint, because I want to show you guys, here I'll show you over here, how you would notate a restriction function if you're not working on Desmos. So let's say we have f of x is equal to x squared. All you would do, you do a colon, so that's the dot and the comma, and then you'd put your restrictions. So if I want to go between -1 x and 2, that's all you would do. Just this, the semicolon, and then this right here. That's all you need. So that should be everything that you guys need for your packet today. If there's anything you're confused about, feel free to ask Ms. McLaughlin or myself when I come back on Monday. And once again, have a great weekend.